Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Computing in Civil Engineering. In the last lecture, we discussed about the interpolation method, and in the process we discussed two methods. One was without the derivative and the second one was with the derivatives. Now in real world engineering problems, in many cases it is difficult to find the derivative because of the nature of the problem or because of its complexity in estimating the derivatives. However, still we see that the derivative based methods are quite popular and quite effective, provided we can estimate the derivative in some or other format for the given optimization problem. Today we are going to discuss three such methods where we need the derivative and use those derivatives to interpolate a point which eventually help us to optimize the given objective function or reach closer to the optimum value, meeting the precision which we have set. If you recall, during the classical method of optimization, we discussed about the necessary conditions to find out the optimum point of an objective function. The necessary condition led us to the point where the slope of the objective function is expected to be 0. With that understanding, today we are going to discuss the three methods where we are going to use the first order derivative and interpolate points between a given boundary in such a way that we reach very close to the optimum solution. For this process, first we have to understand the Taylor series expansion of an unconstrained single variable objective function about a point xi, and this is going to be represented as shown in this equation. Now if we do the first order derivative of this Taylor series expansion, we can represent this particular equation as shown here. And in this equation, if we neglect the higher order terms, any terms beyond this point, and then set the first order derivative to 0, because this is the point where the objective function is expected to have a slope to be 0, then we can rewrite this particular equation as this. In this, if we try to see that this x1 is an approximation to the minimum of the objective function, then a better approximation can be obtained in each iteration by this particular equation, and this particular equation is derived from this particular relationship. So with this common understanding, we'll start our derivative based interpolation method using the Newton-Raphson method. It's a very simple method. In this method, we start with the point x1 and decide a small number representing the precision for the first order derivative of the objective function. At this point, we set the counter I is equal to 1 and compute the first order derivative at the new point which we have obtained. Then we look into the second order derivative as well at that particular point. Once we find the second order derivative, we can find or refine the point by the equation which we had discussed in the previous slide. Once we find the new point using this equation, we find the first order derivative at that new point, and if the first order derivative representing the slope at that new point is more than the precision level we want to achieve, then we set the counter I by increasing it 1 and go to the step 2 where we again find the next point. This process continues until we obtain a slope at the new point which is lesser than the precision we want to achieve. Once we do that, we are going to terminate and report the last point which we had obtained as the optimum point with the objective function value at that point. In this, as we said, that we need to do the derivation. However, there is also a roundabout way without doing the derivation of the two derivatives, which is the first order derivative and the second order derivative. In this case, again we can use the Taylor series expansion and rewrite the first order derivative as this function. Here we are going to evaluate the objective function only in the neighborhood of the given point to obtain the first order derivative of that objective function at that particular point. Similarly, the second order derivative can be rewritten as this way. Here, one of the important parameter is the delta xi. Generally, we select it a small number to represent, and this number we can easily consider as 1% or less of the point at which we want to find the first order and the second order derivative. So this is second order derivative, and we continue the process. Let us see an example using the Newton-Raphson method. We are going to minimize this objective function, and we are starting with an initial guess as 0.5, and we set the precision of the slope as 0.2. Then at the first point, which is here, we find the first order derivative, which is here, and the second order derivative. Based on these two derivatives, we estimate the new point and the slope or gradient of the function at that new point. Once we look into this new point, we find that the slope is larger than the precision which we have set. Hence, we need to go to the second iteration, considering this new point as my point here, where we do the first order and the second order derivative, and based on these two derivatives and this point, we get the next new point. And the process continues in the same way until we see that the slope or the gradient at the new point is less than the precision we had set. Once we reach there, we stop and report the new point as this and the corresponding objective function value as the optimum value. Now the same problem, if we start with an initial guess of negative 0.5 with the same level of precision, we can see that once we obtain the optimum value, the point is actually different. It is positive 2, earlier it was negative 2. So it is quite interesting. How can we get two different values for this given objective function? For this we need to understand, or we need to explore the graphical representation of the function. In the graphical representation, if we see the objective function value of the given problem, we'll see that between negative 3 and positive 3, it looks like this. So in the first case, when we started at 0.5, which is somewhere here, and as we reach, we see that there is an optimum value. However, it is a maximum value at this particular point. So it reached this point and found that the slope is almost 0 and reported this point as the optimum point. On the second example, when we started the point at somewhere here, and as it chose this direction, it reached to the point here, and this location the slope is almost 0, or at this particular location the gradient is 0, and hence plus 2 is reported as the optimum point. So it is clear that if you are using the Newton-Raphson method, we may not have a better control over the direction where we want to go. For that purpose, we may look into or explore other methods which we are going to discuss after this. One such method is the bisection method. In the bisection method, we are going to evaluate only the first order derivative. If you recall, in the Newton-Raphson method, we had to evaluate the first order derivative as well as the second order derivative. There are numerical methods to estimate the second order derivative in case if we cannot differentiate the function. However, in that process, as we saw, we need to evaluate 3 function values. However, we can actually use the first order derivative information much more effective way, particularly if we know the boundary of the optimum point and find out the optimum solution. And in this case, it is not going to go out of bound like what we saw in case of Newton-Raphson method. Depending on the start point, the solution can go in either direction. So in the bounding phase method, the algorithm starts almost in the similar way, where we choose a point xi with a small number epsilon representing the precision for the first order derivative and step size s. At this point, we evaluate the first order derivative and set the counter k is equal to 0. If the slope is positive, then we need to go in the opposite direction for the second point, so we set this. Otherwise, we need to go in the same direction, we set this, and find the first order derivative at the new point in the step 2. Now in the step 3 we need to find out the slope at the 2 points which we have chosen so far, and if we find that the slopes are of opposite nature or the gradient is of opposite nature, then we can start the process of bisection method. If not, we have to look for another point, and as you saw that we are using the bounding phase method to find the new points. So we need to move back to the step 2 to find the new point. So again, these first 3 steps are needed if we do not have the bracket. If we have the bracket, then we can start from step 4. So in the step 4, we are going to find out the average point or the middle point of the 2 bracketing points, which is x1 and x2. So once we find that, we find the slope at that particular location. If the slope is within the precision limit which we have set, then we need to terminate and report this new point as the optimum point with an objective function value at this location. If it is not terminated, means the slope or the gradient is more than the precision which we have set, then we need to see the nature of the slope. If the nature of the slope or the gradient is negative, then the lower boundary x1 is moved to this new point, this average point, and we go to step 4 to find a point, and the process continues. In other way, if we find that the slope at the new point was positive, then the other boundary or the boundary on the higher side is moved to this new point, and we go to step 4 to continue.